Queen's University, Belfast offer holder day. So we went up on the train, we found our hotel. This was all the day before. We went and checked out the buildings. We had to do a recce because it was a new city and I didn't want to get lost. So this is the building where they have their chemistry. It's called the David Keir building. It's not named after a chemist, so I don't know why it's called that. Speaking of Keir, we came across this poster, which looks like Irish Keir Starmer meets Liam Neeson and Maggie Thatcher's puppet thing from Spitting Image. So that's always fun. Then we went and had something to eat, and I had this. Now, it's a milkshake of some kind, but I cannot for the life of me remember what was in it about a week later. But I do remember I liked it, so shout out all the Maggie Mays in Belfast. We did some more exploring. This here is the Lanyon building. It's their main kind of building. They don't use it for lectures or anything, but it's all the graduation ceremony stuff. It's also the building in all of their photos online, and for good reason. It is a very pretty building. Then we came across the Seamus Heaney Centre. Now, I don't know what they teach here, and it was closed for that weekend, but Seamus Heaney is one of my favourite poets. Obviously, he does the Power and Conflict poem, Storm on the Island, and also, for my year of GCSEs, he did the Unseen poem, which was Scaffolding. So, of course, he also gets a shout out. Shout out Seamus Heaney. So, we went back to the hotel, check it out, very cool. And then the next day, we went to the offer holder day. Got this very cool bag that says Queen's University Belfast on it and a map and things. Went and found the chemistry building. Like I said, we did that yesterday so we wouldn't get lost. And we found something called the Chlorine Gardens, which was attached to the chemistry building. But who calls something the Chlorine Gardens? So then we went to the actual chemistry lecture taster thing. And we had a walk around the labs and they showed us some practicals, which was very cool. We'll get onto both of those in a minute. Walked around some more, found this very cool statue of Mr. Galileo Galilei. More walking around, found the library, which has this awesome Mandarin section, something called the Complete Library in 4 sections. Now, I don't speak or read Mandarin at all, but if I did, this would be very, very cool. It is still very, very cool, but I can't use it. Also found a set of books called Learning from Accidents and Lessons from Disasters, both in the chemistry section of the library. And boy, howdy, that is not encouraging. Especially for someone whose practical skills leave a lot to be desired. Did some more walking. There was quite a lot of walking, and found the beautiful, beautiful botanical gardens that they have in Belfast. Well, this was my first time in one of these botanical gardens, and oh my goodness, it is very, very warm and very, very humid. But also, all of the plants are absolutely beautiful. And that was pretty much it. We went to the airport and we got out of Belfast. But now on to the lecture. So we had a lecture on how chemistry can help the world develop, and it started off by talking about the UN's 17 development goals and how chemistry can help solve each one of them. Moved on to the work of this man. His name is Thomas Andrews, and this guy is certifiably amazing. So he studied maths and was taught by the Kelvin Stad, who by the way has a statue in the Botanic Gardens that I'll show later. He qualified as a medical doctor whilst teaching chemistry. He became the first vice president of Queen's University of Ireland, as it was then known. In 1847, he set up soup kitchens to help during the potato famine, and he turned down a knighthood for what he said was for reasons due to his poor health, but what his friend, the Michael Faraday, said was because he was anti-materialism. He didn't think it was important because it wasn't science, so he didn't want it. I mean, what a guy. He, as a chemist, was interested in thermodynamics and physical chemistry, and he's credited with the proof that ozone was an allotrope of oxygen. And what that means is he proved that ozone was just made up of oxygen. Also, a quick side note, while doing research for that bit, I found that Thomas Andrews was also the name of the designer of the Titanic, which is also a very famous thing that came out of Belfast. So, through the electrolysis of water, you produce electrolytic oxygen, But the problem is, with this, you also produce a small amount of carbonic acid, but this carbonic acid is still enough to ruin the rest of the experiment. And the problem this creates is that your ozone that you've created with your electrolytic oxygen reacts with potassium iodide that you're about to bubble it through, and the carbonic acid is absorbed by the K plus ions, and so it affects the experiment. By adding some dilute hydrochloric acid, you just end up with electrolytic oxygen, and this is exactly what we want. So we bubble our electrolytic oxygen through our potassium iodide, which decomposes our ozone and sends off iodide ions, and the H2SO4 prevents any moisture escaping. So anything that isn't the electrolysis equipment is weighed beforehand, and so the increase in the weight is equal to the weight of the ozone. The iodide is converted to its oxygen equivalent, and so you find the weight of what's called the active oxygen, or any oxygen that takes part in the reaction. And because the mass of the active oxygen is equal to the mass of the ozone, we know that ozone is just oxygen. He's also known for his work on the liquefaction of CO2. Liquefaction just means liquidation, but it's used for gases. It also led to the coinage of the term critical temperature. Now here's how he did it. He used this apparatus here, and the little screws at the bottom mean that the pressure and the volume vary. So you can prove that the product of the pressure and volume for one gas is equal to the product of the pressure and volume for the other, and that led to this graph here. So when you plot your pressure versus your volume, you get a graph that looks like this. So anywhere with little dashes under it, that's the unsaturated vapor. Anywhere with the dots is the saturated vapor and the liquid, and then anywhere beyond that point that doesn't have a pattern is a liquid only. And that means you can find the critical point and the critical isotherm and the critical temperature. Now the critical temperature is that it won't form a liquid no matter how high you turn the pressure. The critical point is the highest possible temperature where liquid is still present. The critical isotherm is just that kind of line between them. Then, if you plot pressure volume against pressure, you end up with something that looks like this. It generates what are called ideal isotherms. Like I said earlier, isotherms are just kind of lines. And 50 degrees Celsius is a Boyle's temperature. And what that means is that the isotherm is flat. Now, above the Boyle's temperature, the molecules are closer together, so the pressure increases. Therefore, the change in volume is much more significant. Whereas, and below the Boyle's temperature, it's slower because the attractive forces have more effect on the molecules, and so they reduce the impact and therefore reduce the pressure. So Andrew's work inspired the fridge, and it inspired the state equation, which was created by van der Waals, which you can see below. And obviously it uses gas laws, which he helped influence with his work on critical temperature, critical points, etc. And also the university had one of his original compressors, which was very cool. Now on to the work of another famous alumni, Mr. A.P. De Silva. Now, he was also a professor at Queen's, and he's credited with work on fluorescent PET scans, or as his paper says, fluorescent pH indicators based on photo-induced electron transfer. Now, a standard fluorescent PET sensor consists of 3 parts: a fluorophore, a spacer, and a receptor. The receptor binds to the analyte, that's the thing you're trying to find, and the fluorophore emits light when it's excited. The spacer doesn't really do anything, it's kind of just there. And some of these can alternate signals, a bit like a NOT gate in computer science, and we'll get into that a little bit more later. So when it is, quote, off, electrons are transferring from the receptor to the fluorophore, whereas when it's on, when there's an analyte in the receptor, these electrons don't move, and so it gives off the opposite to what you'd think it would, hence the whole reverses kind of thing. The transferring of electrons obviously generates radical pairs, and these need to be stabilized, and so you can use a polar solvent. But the problem was that most of these were single use, and that's what they were trying to solve. So there are loads of problems, and we'll go through them now. So, orientation determines the rate. Obviously, if you're trying to attract an electron, then if you've got the negative side closest to the electron, it has to turn around so the positive side is next to the electron, so that's going to take longer than if the positive side is just next to the electron right away. They found that at 80 Kelvin, orientation froze and any fluorescence came back. So they also discuss pH dependency and how that affects the rate. And I've written here silica bound, but that's not always the case. In the paper, which I will link in the description, they use about 16 different molecules. Some of them are silica bound, some of them use PVC, some of them use aminocellulose. So definitely go and check it out for yourself. And what was interesting is they said that some receptor fluorophores act as computer science logic gates. So here I've drawn a yes gate, which they specifically mention, and a pass one gate, which again they also specifically mention, which didn't know that was a thing, but it's very cool to read about. And they also talk about animal psychology and things like that. Lots of things that you wouldn't think would be chemistry, but are really interesting to learn are. So that was just kind of a long tangent. They mentioned them as alumni, but they didn't mention any of their work. I did that as research because I thought it was interesting, and obviously for you guys. On the actual lecture, we talked about medical chemistry, and we talked specifically about cystic fibrosis. So cystic fibrosis is a problem you can get in your lungs. So if you have healthy lungs, a cross-section of them looks a bit like this. There's an airway wall, and then there's a very thin layer of mucus. Whereas if you have cystic fibrosis, this mucus becomes hardened, and it becomes quite thick, and it becomes far too sticky. So much so that it sticks to the little hairs that line your brachia and any other kind of airways in your lungs. And this is a major problem because when you get bacteria in you, it gets trapped on the little thin layer of mucus, and then when you cough, if you've ever coughed up like yellow or green, it's all the mucus and it's trying to get rid of a bacterial infection because the bacteria gets stuck to the mucus and then you kind of kick the mucus out of your body. However, with cystic fibrosis, it gets stuck to the hairs and it won't move, which puts you at a double risk. A, because you've got narrower airways, because you've got this big build-up of mucus, and second of all, it won't shift. So if a bacteria gets stuck to it, it's going to stay in your body and it has a higher chance of replicating and causing you proper harm. So chemists synthesized this, and what this does is it acts as a sort of artificial mucus. It sticks to the hairs in your lungs, and then when bacteria come along, they stick to it, and then when you cough, it dislodges and the bacteria comes out with it, and it is called phenylboronic acid polyethylene imine. And like I said, it acts as a sort of artificial mucus, so it doesn't get rid of the airway blockage, but it does get rid of the bacteria problem. So you cough, and instead of the mucus, the PBAPE comes up, as well as some bacteria, of course. So we went down to their labs and they showed us 4 practicals. They did the cannon fire practical, which is where you burn ethanol and then you add hydrogen peroxide and potassium manganate, and because they add oxygen to the fuel, they burn a lot more vigorously. If you've not seen it, it's very cool. Definitely YouTube it. We did the liquid nitrogen on the human breath experiment. I blew up a balloon and he dipped it in liquid nitrogen and it froze. So I got to see my liquid breath. That was quite cool. Although I didn't get to keep it, so maybe it wasn't that cool. And then we did the screaming jelly baby one, which is where you add potassium chlorate to a jelly baby and it burns massively. And I learned during research for this bit that the Americans call it the growling gummy bear experiment, and that is disgraceful. And then the 4th one, they did a thermite reaction, as in they got a first year and got them to light the fuse to a thermite reaction. And the guy who led the experiments did this very cool thing where he went, watch it, and it burnt. And then he went, as you can see, it burns quite a lot. So much so that the aluminium can that was holding all the reactants is gone. There's no more aluminium can. And that was really cool. Oh, and here's the Kelvin statue, because I almost forgot. So that's it. Thank you so much for watching, guys. It's nice to be back, and I will hopefully see you next time for Lancaster Offer Holder Day. Please remember to like and subscribe. As always, thank you to the staff at the university. I had a great time, and I'll see you guys around. Thanks for coming. Bye.